we're going to finish up graph algorithms to the extent that we'll discuss them this month today. And we're going to finish up the shortest path algorithm discussions. There's other graph algorithms that are worth seeing, and we'll run advanced recitations on them if you're interested. By the end of today, I will shift over to a different application, to geometric algorithms. And we won't go as much in depth with them as we have with graph algorithms, but we'll do kind of a little bit of an intro, a little bit of a digging through the cave of geometric algorithms. And there's a deep cave there. You can take a whole graduate course just in geometric algorithms, but we'll just get some of the ABCs done and do the basic algorithms, the sorting algorithms, quote unquote, of geometric algorithms. And then we're shifting gears after that to techniques. And when we talk about different techniques of doing algorithms, we're going to use examples from all these different applications, and even from applications that we haven't discussed as a separate topic. So we'll see examples from graph algorithms again. You'll see examples from geometry. You'll see examples from mathematical algorithms. And you'll see examples in string matching, and in searching and sorting, and in scheduling. So when we talk about techniques, the examples will be very, very broad and not necessarily from the specific applications that we've dealt with so far. Getting back to shortest path. In the shortest path algorithm, there's one main idea, and it's a greedy idea. It's a greedy strategy. And the strategy says that we're going to keep track of current distances and the parent of the shortest path tree, and we're going to update it as we move along. And we're going to update it in this greedy way in the sense that we're going to look at local phenomenon, and if we can do a little bit better, we'll improve the distance values and the parent values. And if we can't do better, we'll go on and look at some other local feature. And when we're all done looking at all these local features, we'll have the overall best shortest paths. And I mentioned to you many times that you can only do this if there's no negative cycle in the graph. If there's a negative cycle in the graph, nobody knows any good polynomial time way to do it, and this local greedy strategy won't work. Instead, you'll either get wrong answers or an infinite loop, depending on what your algorithm tries to do. The first version of shortest path that we talked about is originally due to Dijkstra, although he didn't, in his paper, originally talk about the implementation. So the priority queue implementation and the heap implementation came after him, but he originally talked about this algorithm in the early 60s or late 50s. And it's a very, very basic idea. We're going to do our little local greedy improvement in a particular order. And all shortest paths are basically deciding, let's do it in a different order. So here's what the local greedy strategy is, and I'll review how Dijkstra's order goes, and then we'll shift over to different kinds of graphs and talk about different kinds of scanning orders, ones which work for different kinds of graphs. So Dijkstra decided he's going to use this greedy strategy, and everybody's been working on this one since, and it works like this. It's a very intuitive idea. You scan a vertex, which means we're going to focus on a vertex, look forward, and make local changes in all the vertices that it connects to. So scanning a vertex means looking at all the other nodes that are adjacent to that V, all the U's that are adjacent to that V. And for every one of them, we're going to basically say, hey, look, we know that the current best way to get to V is distance of V. So now we'll scan forward on the edge that goes from V to U. We'll look at the weight. We'll add it to the best way to get to V. And we'll see, is that better than the current best way we have of getting to U? Are we better off going through V and then following this edge than we were going directly to U through some other method that we had previously calculated? And if we are better off taking the combination of these two, then we'll do it by remembering that the distance of U is now equal to that. It's not as bad as it used to be, but now it's better. So we change it, and then we change the parent of U to say that it comes from V, that the best thing to do is to come from V. And this is a review, and this is what we did last time. So you do this for all the nodes that are adjacent to V, and when you're all done, you've made some changes in the distances of these nodes that were connected to V, and then you move on and you have to scan some other node. When do you have to scan a node? If we scanned V, and later on when we're scanning other nodes, V never ever got changed, the distance of V stayed the same, then there's never any reason to scan V again. We've already checked all the edges connected to V and checked whether distance of V plus weight of UV is better than them. These other distances are only going to get smaller, so unless distance of V ever goes down later on, we have no reason to scan it again. Right? That's an important thing to realize in shortest path algorithms. And that's what makes these algorithms run efficiently and finite, and make sure they don't go into infinite loops. In Dijkstra's algorithm, we always scan the node which has the currently shortest distance, which has the smallest one. And it turns out that if you do that, then once the node is scanned, you never ever relabel it or change it to a smaller value. And there's a theorem that states that, and you can prove it. So if you're really careful to do the right ordering, then when you have just positive edges and you're always picking the next vertex that has the smallest current distance, that vertex never gets relabeled or rechanged again, and hence you never have to scan it again. So what we do every time we scan a vertex in Dijkstra's algorithm is we take it off the heap of possible things to scan. We never ever look at it again. We never relabel it again. We never scan it again. And that's why Dijkstra's algorithm takes an efficient amount of time. We scan every node exactly once. This takes one if statement worth, and the only amount of time that this requires is if you're using a heap, then it takes log n in order to change the value of the distances that are sitting on the heap. So E times log n, and that's the complexity. That's review, and that's what we talked about last time. All right, so there are questions about that so far. Yeah?
It's the way VU, isn't it? Because it could be a directed graph, and you're trying to get it.
Yeah, it's... Yes. Absolutely. I was thinking when I wrote this that it was undirected and it doesn't matter, but you're right. If it was undirected, then I should use little curly brackets, and if I'm using the round brackets, then I should make them the right direction. The edge goes from V to U, and you're right. Other points, questions, thoughts? We did an example of this in class. We did an example in review yesterday as well, and there's other examples done in the text, and you can look at them. We're going to go through this idea again now, but we're going to talk about different scanning orders for different special cases. One special case is the graph has all positive numbers. That's Dijkstra. The next special case is the graph could have negative numbers, could have positive numbers, but there are no cycles in the graph. It's a directed acyclic graph. Right? That means if it's a directed acyclic graph, what can you do to a directed acyclic graph that we did 2 algorithms for? You can topologically sort it. Okay, you can put it in order so that all the edges go in one direction, one after the other. You can take all the prerequisites first and then take all the courses after those prerequisites afterward. So what kind of scanning order do you do if the graph has a topological order or if it has no cycles? The key thing is we want to make sure that we scan in such a way that we never have to scan a node once we've scanned it. That once we've scanned it, it's done. It's finished. So what order should we scan nodes in if they actually have no cycles? I'll put a graph up here that has no cycles in it. This graph has no cycles. In fact, that's a topological ordering of it. All the arrows go from left to right in a nice line. What order should you scan these things to make sure you never have to scan a vertex more than once? Well, if we scan it in this topological order like I just wrote it in, if this guy gets scanned first, then these two things get labeled. And then if I scan this one next, then this might get relabeled and that might get relabeled. But I'm never going to have to rescan this or this once I scan them because, how come? Because nothing goes back to them. It's not even as complicated as Dijkstra's theorem that says if you pick the smallest one, somehow you're never going to ever relabel it. Even though you might look at it, it won't get relabeled. Here, you're not even going to go back and see them again. There's no chance you're ever going to relabel them because there's no edge that ever comes back here and goes forward from some other scanned vertex. So as long as you do it in topological order, you're guaranteed never to see these guys again. Scan them, goodbye. This algorithm is so kind of old and somewhat obvious that nobody knows who invented it. It's in the folklore of algorithms, like a lot of algorithms are. And it's basically, how do you do shortest path on a directed acyclic graph? And the answer is do the same thing we did before, but do topological order scanning. So the first thing you do is take your graph, find a topological order, make a list of the nodes in that order, and then run through this scanning algorithm in the order of those nodes. Okay. Are there questions about that so far? Since this can have negative edges on it, or positive edges, because there's never any negative cycles in a graph without cycles, This idea actually works whether there's positive edges or negative edges, because we still never relabel anything once it's been scanned. So it can have negative edges, and it's just fine. Because of that, if I ask you the question, what about the longest path? On the exam, you had a question, the longest path on trees. Okay, that's not an easy question. It's an interesting question. There's a lot of ways to do it. The most efficient way is kind of tricky, and the least efficient way is at least something you can come up with on the spot. But what about this? What about a graph, something that's more complicated than a tree? How would you find the longest path from here through the graph? Well, all you have to do to find the longest path is to take all the edges you have and turn them into negatives, and then run the shortest path algorithm on that. And whatever you get shortest when you make the edges negative will actually be in real life the longest path. So you can find longest path in something like this, because there's no problem having negative edges on it. Anytime you can put in negative edges, you can always change the shortest path to a longest path by changing the edges before you run the shortest path, switching them positive to negative, negative to positive. So you can solve longest path. You can do it on a directed acyclic graph. And it's as simple as saying, take all the edges, change their sign, run the shortest path algorithm with topological scanning. Right? And that's going to solve longest path on a directed acyclic graph. So don't think longest path is always hard. It's easy if there's no cycles. It's easy if you can do the shortest path in the presence of negative edges. That's the moral. All right, before I go on and spend a little more time on the next special case, I want to go back and at least talk very, very briefly about the question on the exam that you did yesterday, because it's a really cool question, and I want you to at least see at least a different way to think about it now that you have some time to think about it. You should be able to come up with some solution to that question. And here was the question. The question was, you have this big tree. Think of it as undirected in the sense that you can go anywhere in this tree from one place to another. Or think of it as directed, but there are children pointers and parent pointers. You can go any place you want in this tree. And the question is, what's the longest path through this tree? Okay, this is a well-known notion, and it's called the diameter of a tree. Right? And as I mentioned before, you're given one spot called the root. So that's where you enter this tree. And then from there, you have to work through these pointers and find the longest path. There's a lot of ways to try to do this. If you just do it brute force, you should come up with some kind of an order n squared, or n times the edges way. And if you think about it very, very carefully and you end up being clever on the spot, you might even come up with a linear time way. But whichever way you came up with, and I want to talk about the brute force or the other ways, we can review those in recitation, but I do want to just talk about one very, very interesting way to think about it that sometimes people think about who don't have any background in algorithms. And here's what I mean. Let's say somebody gives you a big, big tree like this, but instead of writing it on the board, they build it out of string and beads. So the length of the string are proportional to the weights on the edges. So if this has 8, they'll make this 8 inches, and if this is 4, they'll make that 4 inches, and they'll just construct it. Okay, it's actually a good thing to do in middle school, because kids spend a lot of time doing this. They get a big kick out of it, and those that can't really think analytically so well at that age, at least they like to build stuff. And there you have this big, big contraption, and you build a big one, right? And you don't tell them what it's for. They just build it, and you have this big, big, big box, and it's filled with this huge string contraption with beads on it. And then you throw it at somebody, and you say, okay, find the longest path in this contraption. So how do you do it? So they start pulling at it and stretching it, and people pick it up. It's hard if it's a big thing, because you lose track of where you're up to. So here's one way to do it. And it's kind of a handyman's way. If you take this big contraption, and you find any bead at the end, you're certainly not going to get the longest path from a bead in the middle. Right? Because you can always go to that point and keep going somewhere else. So a bead in the middle isn't going to give you the longest path. So you go to someplace on the end, and you hold the thing upside down like this, and you shake it until it all filters down. So is that going to give you the longest path from there to whichever one hangs low at the bottom? Not necessarily, because it could look like this. If I picked up this one, then this is clearly the longest path. And from here to here is not as long. So it's not enough just to hold it by one end and shake it until it goes to the bottom. All right, but now this is enough, and you have to do a little abstract math proof to convince yourself of this. It's not so complicated, the proof. You just need to actually do it to convince yourself. But if you do this once, and then have one of the kids grab the one that's hanging lowest on the bottom over here, and hold that up high, and let the whole thing hang down again, then that will give you the longest path. You have to just do it twice. Pick up the contraption, hold it up, shake it, let somebody go to the bottom, pick up the one that's hanging on the bottom, and shake it again. And then the distance from the top one to the leaf that's hanging on the bottom will be the longest path in the tree. Now, how do you really do it in an algorithm? You have to think about how you do something like that. Do some kind of a search, do some kind of recursion. There's a lot of different ways. But at least intuitively and practically, if you think of this as a physical apparatus, that is an algorithm that you can simulate with your normal data structures. Okay? And the question of why it's true is not so complicated. You can kind of convince yourself. If you do it twice, you can convince yourself that this has to be the longest path. And the proof is a proof by contradiction. If it wasn't the longest path, then, and etc. I won't go through it because it's, we can't, I'll be happy to go through it, you know, maybe in a review or a tutorial recitation. But it's not really, I don't want to spend too much time there. It's a one-line proof. It's not hard. All right, questions about that? So I wanted to show you this because it's a cool proof. It's a neat result. Yeah.
Yes, a good question. What is the real difference between a tree and a graph? If I see this thing you draw in the background, I wouldn't be sure if you're talking about a graph of a tree.
Well, every tree is a graph,
Okay.
but not every graph is a tree. A tree is a special graph that doesn't have a cycle in it. So what makes a tree is that when you go down one way, you're never going to get a back edge. If you're doing a depth first search on a tree, there's no back edge. So trees have no cycles.
There's only one path connecting any 2 points.
Exactly. Right. That's, if you define a tree as something without cycles, then you can prove a theorem that says between every 2 points in a tree, there is a unique path. So when you talk about, you never talk about shortest paths in a tree. You talk about the only path. There's only one path between any 2 nodes in a tree. Yeah.
Well, it's only true that if it has if it's a directed graph, you can have more than one unique path without a cycle, and so that's not a tree, but it is an acyclic graph.
Yes, that's true. Right. So for directed graphs, the definition of a tree is that the underlying undirected structure has to have no cycle. Right, right, right. For directed graphs, you can have graphs that have no cycles, but still are not trees. Like this graph, that has no cycle, but that's not a tree. Something's a tree if the underlying undirected graph has no cycle. Take away all the arrows, then the underlying graph has to have no cycle. Okay, good, Dora? Chris made a good point. That's true. So for directed graphs, there's 3 stages. There's things with cycles, there's directed acyclic graphs, and then there's trees. This notion of the longest path is actually a notion that comes up in graphs too, the diameter of a graph. But there, it's a little trickier because there isn't a unique path between every 2 nodes. So the definition there is, take every 2 nodes in your graph, find the shortest path between them, and the longest of those is the diameter. So imagine you're in a town, and every 2 people in town know the best route to take from their house to everybody else's house. Then the longest of those routes is the diameter of the town. It's the longest you'd ever have to travel to get from one place to another in the town, assuming you always took the best way. So it's the max of the minimum shortest paths. Max of the shortest paths. That is a different problem and much harder than figuring out the diameter of a tree. I mean, you can certainly just do it by finding all pairs of shortest paths and doing a maximum. But the question is, can you do it faster than that? How long would it take you to find all pairs of shortest paths, assuming they were all positive edges? You'd have to run Dijkstra's algorithm how many times? 1 time for each of the starting points. So it would be n times e times log n. Or if you use the n squared version, it would be n cubed. So our goal in the diameter of a graph algorithm would be getting it better than n cubed. Right? Okay, questions about this?
When you say diameter of a graph, can you apply the term diameter to all graphs or just to trees?
To any graph. For a graph, you have to define it a little more carefully. We mean that take every 2 nodes, figure out the shortest path between them, and take the biggest of all those numbers. That would be the diameter of a graph. That would be the same for a tree, except in a tree there's only one path, so there's no shortest calculation you have to do. And you can definitely do it in linear time for a tree. The question is, can you do it? How fast can you do it for a graph? That's a hard homework problem. And going through this example is really important because you'll really see just what might go wrong when there's a negative edge. Okay. Let's go here. Distances. A, B, C, D, E, F. Okay, here's a graph that has negative edges in it, but if you look really carefully, there are also cycles in this graph. Right? Here's one cycle. Okay. There should be another one.
CD.
Oh, here's another one. Yeah. Okay. Here's another one. There's a few cycles in this graph. None of those cycles, if you add up their weights, should be negative. If there were, then we wouldn't be able to do this problem correctly in polynomial time. And you can check that none of them are. This one's 0. 0 is OK. But it can't be negative. This one is, it's not a cycle. This one is 1. OK. Oh, I didn't have that one. I thought there was another one somewhere. I got a big one. No, that's it. OK. So some of the cycles are one's 0, one's positive 1, but none of them are negative. So we can definitely do the shortest path algorithm on this, but which order should we scan the nodes? That's the question. We're going to do it. Our starting point is A. That's arbitrary. And therefore, we set the distance of A to 0 and the distance of all the others currently to infinity. As far as we know, we can't get to any of them at all. We haven't looked at any edges. We haven't scanned anything. Okay. This method I'm going to call breadth-first scanning, because we're basically going to do a breadth-first search of this graph and scan the nodes in that order. Now, it's equivalent to what the book calls the Bellman-Ford algorithm, but the Bellman-Ford algorithm doesn't go out of their way to scan in any particular order. So what they do, I'll show you at the end, is just scan in any order, just do it enough times. And that's a little less easy to understand than this. It's easier to understand the algorithm, but much harder to understand why it works. Here we're going to scan in a particular order, and the engineering of this example will be much faster than doing it the Bellman-Ford way, which will always go through more times than it needs to. All right, so we're going to scan in a breadth-first way, and we'll see what happens. Let's go through it and analyze a little. Scanning forward from A, which two distances do we change? We change B and E. We have 0 plus 1, 0 plus 2, so we can get to B in 1 and E in 2. So this becomes 1 and this becomes 2.
And do we worry about the parents?
We do, but I'm not going to write them in because you guys can do it on your own. It'll take away from the real thing, which is calculating the past. But sure, you definitely keep track of the parents. And both of these would have parents of A. Absolutely. OK, so according to our method, we're going to scan breadth first. Now, how do you generate things breadth first? What data structure do you use when you generate things breadth first? You use a queue. And that's what we're going to have in this algorithm. There's going to be a queue. There's no queue in Bellman-Ford, so that's the main difference. Here we're being very careful about what to scan next. And in Bellman-Ford, they keep scanning. I'll tell you how many times later. I'll tell you the difference between them. So we have a queue. And in the queue, we started off, the queue goes this way. We started it off with A. And then this algorithm basically has a loop that says, as long as the queue's not empty, take the next thing out of the queue and scan it. Anytime you actually relabel something, stick it in the queue. because you're going to have to scan that again. If something's already in the queue and you relabel it, then you can just change its value. You don't have to actually put it on the queue again, because it's already there. It's going to get scanned anyway. Everybody get that? Let me say that again. The algorithm looks at the queue, takes the next thing that's in the queue and scans it. If doing that scanning changed any distance values, then you take those things and you put them on the queue also. So in this case, B will go on the queue and E will go on the queue. And A is now off. Okay? The next thing we'll do is repeat. We're going to scan through B. If that changes any distance values, we'll put them on the queue. Keep in mind, and this is a little bit of a variation on breadth-first search, if say B is scanned and it changes the value of E, let's just say that happened. If that happened, we wouldn't put E again on the queue. There's no point in having E on there one after the other. It's there once, it's going to get scanned. We don't have to do it right afterwards again. So you won't put it on twice. There won't ever be at any time a node twice on this queue. It might come off and go back on again, but they will never sit on the queue at the same time. Yeah, Chris.
Might it turn out, from an engineering perspective, that it's more expensive to figure out whether it's in the queue than to just throw it on the queue again?
No, because you're just going to have some little array. And anytime you put something on the queue, you set that Boolean array to true. Anytime you take it off the queue, you set it to false. So it's very easy to keep track of something's on the queue. There's no search involved. It's just a one-step thing.
Well,
so I think
if it's on the queue, it's just the one step, but to locate it on the queue could potentially be more, because you said you're going to have a Boolean array that's going to say whether it's on the queue, and that you just look up in its location.
Right.
Array.
Right.
But to know whether it's, maybe you've got 2,000 items that are on the queue.
Right.
You've got to search through that whole set of 2,000 items to locate it, to change it, don't you?
No, you change it to the distance array. You've got an array for distances. You've got a Boolean array that says whether it's on the queue or not. And that's it. Two separate arrays. So you don't have to search through. No, there's no... this algorithm can really be done very tightly. There's not a lot of overhead, I don't think. I think you can do it that way. All right, let's go through and continue. If you do it, you'll get a better sense of what's happening. So the next thing we scan is B. Off it goes. What changes occur? B only connects to C. So C becomes, the current distance on C is infinity. The current distance on B is 1. 1 plus 3 is 4. 4 is less than infinity. So C now becomes 4. And now C has to go on the queue. Now I'm going to do this and tell you what they mean later. It's kind of obvious what they mean. I'll tell you what they mean now. When A goes off the queue, it might make a whole bunch of other things go on the queue. I think of all those other things in one group. When all those other things are off the queue, they might have made a whole bunch of other things go off the queue. I think of them in a group. These groups correspond to the levels of the breadth-first search. This is level 0. This is level 1. The vertices that get on the queue because of these two would be level 2. It's a very natural way to think of the things on the queue. It's a slice in time. So rather than just put them without the little markers, these markers are just our own little intuition, but they'll come up later when we talk about the analysis of this. All right, so now I'm going to scan through, which one am I up to? E. E is now off. And what does E connect to? It connects to B, and it connects to F. So let's do B first. That's alphabetical order. The current distance on E is 2. 2 plus minus 2 is 0. Is that less than the current distance on B? Yes. The current distance on B is 1. So I can do better than 1. I can do 0. That's very important what just happened. We've already scanned B before. We've already gone forward from B. And a couple steps later, we're going back and noticing that, you know what? We could have gotten to B better. So now we're going to have to go forward through B again and propagate that information to all the places that B can get to. We never had to do this before. It didn't happen in topological scanning. It didn't happen in Dijkstra's algorithm. In those two situations, when we scanned a node, it had its permanent distance value. It was already correct. We never had to go back and relabel it and then go forward and scan it again. But in the presence of negative edges, you do have to do that. And that's why Dijkstra's algorithm doesn't work with negative edges, because it will never rescan anything, so it can't possibly get the right answers all the time. Here, since we rescan B, B's got to go back on that Q. And on it goes. Notice it's not on at the same time as it was before. It's already come off, and now it's back on. You would never have two of them on at the same time. All right, so now we're scanning. We're still scanning E. We have to scan to F. Yes, John.
If you do want to rescan B, then C should now be 3 instead of 4.
But we haven't gotten the
But we're going to wait.
Oh, I'm sorry.
Right. We will do it, but we'll not do it just quite yet. So now we still have to finish scanning E, and scanning E goes to F, and then F is 3. Right? 5. 3 plus the current distance on E, which is 2. 5. 3 plus 2 is 5. Thank you. And then F goes on the list. And now we finished scanning this level. So now this level is done. Okay? That ends the next level. Notice B got put on again. Let's continue. Now C needs to be scanned. What gets changed?
Is there a way to figure out that we really oughtn't scan C right now because we're just going to have to do it again in the next step?
I don't think so. I don't think there is, because that's only because you've been staring at this graph and you know. And for all you know, actually, I mean, I understand that that's because the best way to get to C is through B. But in fact, for all you know, the best way to get to C is actually not through B, and it's through some other way that we'll find out later.
Right, but we have a parent array, so couldn't we check to that's the case, but see if its parent is on the queue, then we shouldn't scan it right now because its parent is going to update that.
I don't know, and it's certainly a good thing to think about, and I'm not sure if it would help either us asymptotically or engineering-wise. But I know just what you mean, and I'm not sure about the answer. It's a good question. It's a good question. Scanning through C, what gets changed? D. And D becomes 4 plus 2 is 6. And now D goes on the queue. Now we scan B again. And this is what Chris is saying. It seems a waste to bother scanning C because we're just going to relabel C again and have to stick it on. Agreed. Now we're going to scan B. That means C gets 0 plus 3, and that's better than our 4. So this becomes 3, and now C goes back on the list. And now we scan F. And that makes C equal to, current distance on F is 5. 5 minus 4 is 1. 1 is better than 3. So do we put C on again? No, don't put C on again. It's already there. Just change its distance. There's no reason to put it on twice. Once with a 3 and then once with a 1. Putting it on 1 will just subsume the case of the 3. So we just leave it there, and we change this to a 1. That's the current value on C. And we're going forward this way, minus 6. And B was currently 0. And F is 5. 5 minus 6 is negative 1. So we can get to B negative 1. So that's even better. And now we're going to rescan B.
What order are you scanning in? Aren't you doing alphabetical order?
Oh, I should have done B first? Yes, absolutely.
It's okay because C was already there. You didn't put it on the
Right.
Oh, yeah, it's okay because that's true. But you're right. I should have first looked at B, put it on, looked at C, realized it was there, and not put it on again. Although it is right the way it looks. You're right. You're right, Todd. Our convention is to do alphabetical order in the adjacency lists. Okay. I want you to get a sense of this. I want you to realize how many times you have to relabel every node in doing this. It's not okay just to go forward and hope you're going to scan each one once. You scan it. You find out later you got to rescan it. You find out later you got to rescan it. And the question is there any end to this? Can this go on forever? And if there is an end, then how do you analyze what this end is going to be? We're almost done, and you'll see exactly what happens, because this is a super example to see it. Yeah?
When you got 6 going to D for C,
Yes.
is that right? I just don't, why would it be 6?
Because C had a current value at the time of 4, and 4 plus 2 is 6.
Oh, it was still 4? Okay.
Yeah. We are later on going to scan C again and get a better value for D. But that won't happen just yet. It'll happen soon. All right, the Q curves up this way. All right. Yes. It's a curving data structure. Now we scan D. And D goes forward to F, and F's current value is 5, and D's current value is 6. 6 plus 2 is 8. 8 is not better than 5, so we make no change, and we do not put F on the stack. Right. It's nice not to put something on the Q. I said stack, I meant Q. So that's done, and I think here's our next bar. Now we're going to scan C. C goes forward. Its current value is 1. 1 plus 2 is 3. That's better than D's value of 6. So D now becomes 3. It goes back on the stack. Q. Everybody turn. All right. Cross out C. Thank you. Now we're going to scan through B. B goes forward to C. B's value is -1. -1 plus 3 is 2. Is that better than? No, not better. So we don't make a change. OK. Now we scan D. D goes forward to F. No change occurs. Nothing happens. The Q's empty. We're done. Right, D is 3. 3 plus 2 is 5. 5 is the same as F. If it's the same, you don't make a change. Finished. Q's empty. How many phases in this algorithm? Where a phase is one of these levels. 1, 2, 3, 4, 5. That's very important. There is a limit to the number of phases you can have in this algorithm. And I'm going to explain to you the theorem that gives you that limit in just a second. I'm going to convince you that the number of phases here is limited. And it's limited to the number of nodes -1. So there are 1, 2, 3, 4, 5, 6 nodes. You can have at most 5 phases in this graph. You're never going to have more than 5 phases. I'll explain to you that in a minute. But if that's true, let's analyze how long this algorithm takes. Let's say that we never have more than 5 phases in this algorithm. Then how long is it taking? It's guaranteed to end after 5 phases if there's no negative cycle. Well, in each phase, what's the worst that can happen? You could have all the nodes on the graph in that phase, right? How many steps does it take to scan all those nodes? You got to pull them all off one at a time and look at all the edges connected to all of them. That's proportional to the number of edges in the whole graph. So every single phase, in the worst case, if all the nodes were on the graph, would take some time proportional to the edges in the graph to pull them all off. Look at all the edges connected to each one of the nodes. And there are n phases, or n-1 phases. So the total time of this algorithm will be E for every phase times n, the number of phases. And that's the best you can do with this algorithm. That's as fast as it goes. Now, I haven't convinced you. I've just told you that there's a limited number of phases in this algorithm. Before I convince you of it, or at least give you a plausible reason, I won't prove it, but I'll give you a plausible reason. Before I do that, I want to compare this to the Bellman-Ford algorithm. Because the Bellman-Ford algorithm is like a chaotic version of this. Here's what the Bellman-Ford algorithm says. It says, go through every edge in your graph and scan forward on those edges. Don't even do it by scanning nodes. Just pick every edge and scan them all. And when you're all done, do it again. And when you're all done, do it again. And do it n times. The Bellman-Ford algorithm says scan everything and scan everything n times. This algorithm says don't scan everything. Scan the ones that got relabeled. But I can argue that you'll never have to do it more than n times. So the Bellman-Ford algorithm works in kind of this magical way. It just does it n times, and it says when you're all done, that's the best you can do, and I'll prove it to you. Here, it's a little more intuitive. We're only scanning the things that get relabeled, and I'm going to convince you that things that get relabeled never create more than n phases. And each phase is at most e. But notice that this is going to be faster engineering-wise than the Bellman-Ford algorithm. The Bellman-Ford will actually look at all the edges n times. It will be en all the time. Here, we never got the worst case showing up here. We didn't get 6 nodes or 7 nodes on each phase. We got 1, 2, 3, 3, and 1. So this in practice will probably be faster than the Bellman-Ford simple implementation, even though they more or less do the same thing. Yeah?
A little bit confused why each phase is only e times.
Mm-hmm.
Because it seems like each node that we're scanning might potentially have to scan all of the edges, and there could be potentially
N edges.
Every node could be in each phase. We could have.
Yes, right.
So it seems like each phase could be n times e.
Oh no, no, it can't be quite that bad. Here, the worst case, here, say you have this node, Doug, right? The worst case is that it connects to a whole bunch of other...
It connects to all the other nodes.
All the other ones. So the worst case you're imagining is really n squared is what you're trying to say. So you have n nodes.
Well, that one node has to scan all the edges because it's connected to all the nodes.
It scans n. It doesn't scan all e. There's other edges in the graph.
Yeah, it scans n.
So you're trying to say, why isn't it n squared? Why is it e?
Right.
And the answer is that, here, let's look. Let's say the graph looks like this, where there's lots and lots of edges connected to this one. So doing this one takes this proportional time. And doing this one takes that proportional time. And doing this one takes this, 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 this. The time it's going to take me to scan each node is proportional to the number of edges connected to that node. So if I do them all together, I end up getting a total amount of work that's equal to twice the edges, once on each side of each edge. So if I make an analysis like you did of the worst case, yes, worst case it could be n squared, but you know what? If you look a little carefully, that worst case never happens.
But what you're talking about is the worst case of E, not the worst case of Z. The worst case of E is n squared, which means this is running in.
Yes, right. Rob's right, and that's what you're saying. The worst case is that the number of edges actually ends up being n squared, and that can happen. But if it's not, then this will just be the edges. It will never be n squared if the edges are less than n squared. Okay? Is that?
Yeah.
Right. So.
That's graphish, not this algorithm specific.
Right. Does that make sense, Doug? It's an important point, and it's a tricky point that you have to analyze this as a whole unit rather than an iterated case by case, because the iterated case by case makes the analysis not as tight as it can be. You need to think of it all together, and that comes up a lot in algorithms. Yeah.
Some texts seem to call all these kinds of algorithms just order E. Is it common convention to just, if it's En, just to call it order E, or is that wrong?
No. Oh yeah, order E is different than order En, right? I mean.
Yeah. Okay.
Bellman-Ford isn't order E.
But BFS and DFS are order En.
Those are order E. Those are order E plus n. Those are order E plus n. This is order E times n. So this is definitely slower than BFS and DFS. Definitely slower in the worst case. Absolutely. All right, so I'm going to give you the plausible reason why you can only have so many phases in this graph. And here's the plausible reason. In Dijkstra's algorithm, once you scan something, you know it's got the best distance. In topological scanning, once you scan something, you know it's got the best distance because you never see it again. In this algorithm, after phase 0, all paths that have 0 edges have their correct distances. After phase 1, all paths that have 1 edge have their correct distances. After phase 2, all paths with 2 edges have their best distances. It turns out that in each phase, you have the correct distances if you limit your paths to that many edges. So if I stopped here and looked at the picture of our distances at this point, then those distances would be right if we allow paths that have at most 2 edges in them. So the question is, how long can a path be in a graph? If we start from here and go to D, what's the longest path? We can go through all the nodes exactly once. 1, 2, 3, 4, 5. We can't have a path longer than 5. If we had a path longer than 5, there'd be a cycle. Cycles can't help us. unless there were negative cycles, in which case we're dead. But cycles can't help us, so the longest path in here is 5 long. So once you have 5 phases, the number on D represents the best distance for any path that has 5 edges or less. And 5 edges is the most you'd ever have. And that's why after 5 phases, the queue always empties out. Or in general, after n-1 phases, the queue always empties out. Let's look at the path to D. What's the best path to D? Starts here. Where does it go? How do I get a 3 to get to D? A to B, B to... Wrong way, right? A to E. 1, 2, 3.
It's A, E, F, C, D.
1, 2, 3, 4.
No,
No.
C instead of
1, 2, 3, 4. Is that the best? 5, 1, 3. 5, -1. No, this one's fastest. Okay. So the way to come up with an example where this shows up, where you get all the phases, is to try to come up with an example where at the beginning you think your best path is this, but then later on you find out your best path goes through another node, which means you have to do the relabeling. The worst case is that you have to put something back on the stack n-1 times, on the queue n-1 times. All right, so let me stop for a second. Questions about this breadth-first scanning. Let me ask you a question. What if there was a negative cycle here? What if this, instead of it being a 2, was only a 1? Big question mark. What would happen? Find me the step that something weird would happen.
Every time we scanned F from D, we would get a better value.
I mean, every time we scan D and move to F?
Right.
Every time we scan D, say right now. Say we're going to scan D right this second. Current value of D is 3. 3 plus 1 is 4. The best value we know on F is 5. And therefore, we would change F to 4. And then we'd have to put F on the stack. Notice the theorem just goes out the window. If there's negative cycles, it is not true that you get the best result after so many phases. In fact, there's an infinite number of phases to get the best result. Now you have to scan F. The current best value in F is 4. 4 minus 4 is 0. C is 1, so this now turns to 0. You put C on the stack. C is 0. 0 plus 2 is 2. The D moves down from 3 to 2. You put D on the stack. 2 and 1 is 3. The best you can get to F is 4, so this becomes 3. What's going to happen here? You start following these 3 sequences on the queue over and over again. FCD, 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 forever. The theorem blows apart. It doesn't hold. The algorithm blows apart, and it runs forever. It's worthwhile to think about how I can make sure this doesn't happen when you run the algorithm. And if it actually ends up that there's a negative cycle, the algorithm stops and says, sorry, there's a negative cycle. Don't make me run forever. I'm tired. All right? Make it stop. Don't make it go forever. There's a lot of different ways to do that. And, well, I'm leaving that to you. It's one of the assignment problems. So you think about that. The book discusses it, and there's more than one way to do it. More than one way to make this algorithm help you find a negative cycle. Okay, questions?
When you finish this, can you always get the path back?
Yes, because normally we'd be keeping track of the parent. Yes. You just trace back, you get a shortest path tree just like we had before. Same thing, nothing different. It's kept track right over here. Of course, if there's a negative cycle, then what happens is that the shortest path tree loses its tree status, and you get a cycle in the shortest path tree. So, which is one way to find out if you get a negative cycle, is to traverse back on the parent pointers and see if you end up back where you started. It's not the best way. There's actually a little bit of an easier way. Good? Done with this? New topic. All right. So Todd, before you were asking me about Bellman-Ford, do you get the distinction between them?
Yes, I do.
Okay.
Does this one we did have a name?
I don't know. This particular approach and the way of showing it, where everything is just scanning orders of doing scanning rather than a lot of different things, but it's all just different versions of the same idea, is originally written in a book by a guy named Tarjan, who did a lot of these kind of algorithms and data structure analysis. It's a very good book. I have it in my library. It's called Data Structures and Network Algorithms, and he just calls it breadth-first scanning. He gives a little history of where it came about, and the original people who created it were Bellman and Ford independently. Bellman in particular discussed this stuff a lot. So I think this is just Tarjan's presentation of Bellman's algorithm in a way which is easier to analyze. He does a really nice job of stripping away seeming differences between things and making them seem more uniform. So it's a really good thing to read or look at. Our book is okay too, but I like Tarjan's approach better.
Does the breadth first scanning method run slower than Dijkstra's algorithm in a?
Oh yeah. Yeah, Dijkstra's algorithm takes e log n or n squared, and this takes ne.
Well, but
yeah.
in the case where...
Oh, in the case where it's positive?
If it was positive, then you never would update anything, would you?
There's a good question. So Chris asked a question. Let's say all the edges are positive, and you run the breadth first scanning algorithm. Then how long does it take? If you actually go ahead and run one of these scanning algorithms like breadth first or any other one on a positive edge graph, then the question is, do you ever need to go back and relabel something? So the answer is, I think, yes, that you might have to. It's not going to run as fast as Dijkstra because it's possible that a breadth first scanning accidentally will not do the shortest current distance first, in which case things do need to get relabeled and then rescanned. It'll never be worse than NE, but I don't think it's going to be, in general, as fast as Dijkstra. You could certainly do both. You could just say, look, if there's a choice between, it's a little tricky. You can do a hybrid. You can say, look on the queue and take the one that's the smallest current distance next or something. It might mess things up in the analysis. I'm not sure. But the answer is no. It wouldn't run as fast. You can't just do one and have the best of both. Other questions? Okay. Okay. Let's switch topics. Different application. Geometric algorithms. So geometric algorithms are what they sound like. They're algorithms that deal with things that you normally think of as being in geometry. I gave you a version of minimum spanning tree that's really a geometric version that's NP complete. And that was if somebody gives you a bunch of points like this, the question is, where's the best set of points that you can connect edges from those points to these given points and get the minimum weight of all the edges all together? Is it something like this? Is that it? Or is there another better way to do it? So that's a hard problem. That problem is NP complete. That's called geometric Steiner tree. But there's a lot of geometry problems that are not NP complete that you can really do. And they're very practical, and they have applications in chip layout, and they have applications in all sorts of related areas. So what's a good example? Let's do the sorting of geometry algorithms. The sorting of geometry algorithms is this problem. This problem is called Convex Hull. And Convex Hull is best described just by an example. Imagine somebody gives you a whole bunch of points, and they want to know in some sense, what's the border of these points? So this is good if you're writing a Go playing program and you want to get kind of an influence function. You want to see what surrounds other things. You got a whole bunch of black points. You want to see what their border is. So imagine that there were nails hammered in at these points, and somebody took a big rubber band around all the nails and let go. The convex hull is the points that that rubber band would hit. In particular, in this example would be these 5 points. And the convex hull is given to you as an answer in some kind of a clockwise or counterclockwise order. It would be this point, followed by this point, followed by this one, followed by this one, followed by this one. That would be the output of this algorithm. The input would be a list of points. The output would be another list of points, telling you what the convex hull is. Geometry algorithms in general are algorithms that deal with inputs that are either points or line segments or polygons, things that are geometry objects that you want to ask geometric questions about. So very different than graphs, even though they might look like graphs. They're very, very different in how you actually write them. We're going to store them as pairs of floats, just an x coordinate and a y coordinate, a point. A line segment is 2 points. So those are our data structures. The data structures are straightforward. The question is, how do we do the algorithms? How do we do anything with geometry? Okay. We're going to talk about convex hull, 3 different algorithms. One is going to be an n squared, and the other 2 are going to be closer to n log n. Actually, one is going to be n log n, and one is going to be n times the number of points on the hull. So if there's very few points on the hull, that one is going to be linear time. And if there's all the points on the hull, that one will be n squared. So we'll have 3 different kinds. One will definitely be n squared, one will be n log n, and one will be n times h, the number of points on the hull. So this will be better than this one, only when there are very, very few points on the hull, and worse than this one when there's very many points on the hull. The worst case is that all the points will be in the convex hull. And the best case is that there will only be 3 points on the convex hull. That's the minimum you can have. This one is due to Ron Graham, a very well-known computer scientist and discrete math expert and juggler and a number of other things. And this one is due to Jarvis. And this one is maybe folklore. I'm not sure if anybody invented it. We're going to talk about it today. The thing about all these algorithms is that they're all based on some low-level ABCs of how you manipulate geometric objects. And I don't think we can do anything until we study that. So before I go through that, I want to ask you guys a question of what can you figure out about points? Like, how would you come up with any algorithm for convex hull? What would you do? Here's a question I once gave on a programming contest at the freshman, sophomore level in college. You're given a point, you're given 4 points, like this, and you're supposed to find out whether this one is inside the triangle formed by this one. Relatively simple question. This is, I'll put something here, 1, 3. This will be 2, 5, 4, 8, 0, minus 8. The triangle formed by these 3 points, does it contain this point? Yes or no? How do you do stuff like that? Bob, you have an idea?
Well, if you found the angles that were created by the lines connecting each point to each other point, you kind of like do like a clockwise or a counterclockwise scan for points and see whether you catch a point in the containing triangle before the point that you want to see if it's contained when looking at all 3 of the points in the containing triangle. Does that make any sense?
It makes some sense.
You want to make sure that your sonar scan going around your triangle like runs into triangle points from each point before it runs into the thing.
Okay, so it's like doot, 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 bleep, right? That's fine. That's a good visual way to do it. The question is, can we mimic that visual idea with some simple if statement, with some, something that really gets right down to brass tacks and does it? This is more or less the picture of the triangle I drew, right? The skinny little triangle. And is 1, 3 inside this? Well, I think it's kind of easy to see it's not. But even doing it this way and drawing the pictures, it could get so close that maybe we wouldn't be quite sure. It's certainly not an algorithm to make a picture like this. So we need a way. And Rob's idea was what? In this particular example was to start at 1, 3 and to do...
Well, to calculate the angles from the 3 triangle points to each other and the point that we're testing when you connect them with a straight line. That way you could sort the angles. And depending on whether you're going counterclockwise or clockwise, whichever one came first would be either the point of the containing triangle or the test point, which would mean that it was not contained.
Okay. Okay. So Rob's getting at an important thing. We need to be able to tell, it seems it's going to be useful to tell, given, say, A, B, and C, we need to be able to tell whether this thing is to the right or this thing is to the left. Some way of checking orientation between lines. Now we can do that if we actually had the angles, like Rob said, but it turns out that it's inefficient to be computing angles because then we have to do all sorts of trigonometry. And who wants to do trigonometry if you don't have to? So in computational geometry, you want to avoid doing trigonometry as much as possible because it slows you down and it gives you things that isn't necessarily accurate and may be floating point values which depend on the accuracy of your computer. And in very, very close cases, that accuracy might break apart, and you'd think things are equal when they're not. So you want to avoid that if possible. You want to stick to integers. You want to stick to things that will avoid that calculation. So we need to do what Rob suggested, but we're not going to do it using angles. We need a way that avoids it.
We can find
Equation of lines. Let's look at that. Well, first let's define more specific what we're trying to do. Let's say that we want to do this. Here's the point 3, 5, and here's the point 8, 2. We want some function that's going to take 3, 5, and 8, 2 and tell us, say it takes them in that order, point 1, point 2, and tell us whether point 1 is clockwise or counterclockwise from point 2. Whether it's left or right. Okay? If we do that, then we'll be able to at least compare angles. We can even get a sonar scan. You give me a bunch of points, I'll check which one is counterclockwise or clockwise from another, and I can even sort them in order and visit them in order of that scan. It's going to turn out being able to do this one little thing, being able to check whether something is clockwise or counterclockwise relative to another, if one point is clockwise or counterclockwise relative to another pair, that's going to be enough to give us all these algorithms. Right? It'll give us a lot of other stuff too, but it'll definitely give us these algorithms. So we need a way to do this. So you guys are suggesting that I look at the slopes of these lines. So the slope of this line is what? Well, I made a point from 0, 0 here. So, all right, so the slope of this line is 5/3, and the slope of this line is 1/4, 2 over 8, 1/4, right.
Can you just sort on x coordinates?
I don't think so. So, Heather, I can't.
I was trying to think in terms of if you took one point, if you just compared the x and y coordinates, you'd have 4 different situations. One where one point was both things were less than, when x is greater than, but y is less than, y is greater than. And probably for each of those quadrants, you would be able to say it's clockwise or counterclockwise.
Okay, but what test would you do, say, in this quadrant to do it?
Well, in that case, like...
Well, let's work in the upper right quadrant. It'll make things easier for now.
With a triangle, you can just check the intercepts on those lines and find out if it's between all the lines of the triangle, the point that you're looking at. The intercepts on the x and y lines of the point that you're checking.
So you want me to go this way and this way?
Right, and if it and find out what the intercepts on those.
Find out what these are, and if this point is in between those two, and if it's in between the other two, that might be a good way, and that avoids using the angle idea. Agreed. So there are maybe simpler ways of doing particular problems and to avoid having to do the angle idea. And I agree, Brian, that's a neat idea and a neat way to do it. And there's a lot of geometry problems you can try to avoid as much as possible complicated computations. However, once we get into convex hull, we're definitely going to have to be able to do something like Rob suggested. And for other problems, we'll require it too. But your idea is good because the whole spirit of geometry algorithms is to try to avoid the low-level complicated stuff and to try to build everything up out of some really, really simple building blocks. So good. Let's call this procedure orientation. P1, P2. We want a procedure called orientation P1, P2, which takes 2 points, P1 and P2, and tells us, is the first one clockwise or counterclockwise relative to the second one? Okay, so this is what it will look like. If P1 is here, and P2 is here, then this thing should output.
P2 is clockwise.
Right. P1 is counterclockwise from P2. Right.
So
however you want to say it. Right. We'll do it with respect to the first one relative to the second one. This should say.
First relative to second relative to.
It should output either P1 counterclockwise from P2, or it should output P2 counterclockwise. Sorry, P1 clockwise from P2. It should tell you P1's orientation relative to P2. Clockwise or counterclockwise?
And the origin.
And the?
Should it take an origin as an input as well?
We'll talk about that in a second. Good point. This is the simple version. We'll soup it up later. We're just assuming there's 2 points. We want to figure out that we're doing our, our little angle check from the middle. How do we do this? Let's call P1 equal x1, y1, and P2 is x2, y2. So our slope for P1, in this case, is 5/3, or y1 over x1. And our slope for P2 is y2 over x2. Okay so far? And I told you that we didn't want to do division, ideally. So how do we check the comparison between these two? Basically, if this one is bigger, then we want to say counterclockwise. And if it's smaller, we want to say clockwise. Okay? So how do we make a comparison without doing a division? Right, this is from, God knows, the early Middle Ages. People knew how to do this. You take two fractions and you want to compare them. You don't do any division. Actually, the definition of how to compare fractions is this times this bigger than this times this? That's what they even teach in probably, I don't know, what, 4th grade or something? 20 compared to 3. If 20 is bigger than 3, then 5/3 is bigger than 1/4. So that's what we do. We calculate, let's write it out, y1 times x2, and we compare it to x1 times y2. We subtract these two, one from another. If it's bigger than 0, then we output counterclockwise. Bigger than 0, we say counterclockwise. Smaller than 0, we say clockwise. And what if it is equal to 0? It could be. What does it look like if it's equal to 0? Right, good, Dora. They're on the same line, right. Neither one is clockwise or counterclockwise from the other. All right, so we've got a way now, which is really pretty straightforward. It's just multiplications and subtractions and a comparison to 0. It's almost a machine language instruction. We've got a way to figure out, given 2 points, whether one orientation is clockwise or counterclockwise from the other. That's the same as comparing two numbers for our sorting stuff that we did earlier in the year. This stuff has to be understood because all the other algorithms we talk about are going to be based on the ability of answering that question of orientation. So you got to get this stuff down, and we're going to build up from here. Now, Rob asked a good question before because we want to actually do more than just work from the origin. So let's see if we can talk about that for a minute before we move on. Questions so far? Okay. Okay, let's say you're over here at this point. You're not at the origin anymore. And you have an algorithm that says, choose the edge that's the most rightest one. That's the most clockwise one. Okay? That's a typical thing you'd want to do in an algorithm. Make the rightmost turn. Go this way. How do you do that? Well, suddenly we've changed our focus. Instead of being at the origin and wanting to compare this to this, now we're here and we want to compare this to this. Whichever one is the most clockwise, we're going to choose. So this is just like a maximum algorithm. If we could figure out which one of these is the most clockwise, we'd pick the biggest one. As long as we have a way of comparing clockwise and counterclockwise. The thing is, now we don't have the origin anymore. We have it at this point. So what do you do?
Make that your positions.
Right. So anybody who actually remembered stuff from back in linear algebra or who maybe studied physics a little bit, you basically just translate your vectors, as it's called. Instead of dealing with P1 and P2 and P3 directly and using this formula, you take this point, which is your foundation, your comparison, call it Q. Normally, we would just run this formula on P1 and P2 or P2 and P3. But now what you do is you subtract off Q before you start. So if Q was 0, 0, you would just do exactly what we did here. You subtract off 0, 0, nothing changes. But if Q is the point, say, 4, 2, and this is the point 5, 9, then the first thing you do is you subtract these two, and you get 1, 7. And you use that for this point. You'd subtract this from 4, 2, and you'd use that for this point. You subtract P3 from 4, 2 from P3, and you'd use that for P3. And you use the differences. And the comparison between those differences is going to give you the same answers as if you just had this as your basis. So if you change your basis or your origin, just subtract off the origin from your points and continue as before. Okay? All right, let's check to see if it works. Let's do an example, because I see a few confused looks, and I'm not sure maybe if everybody gets it. So let's go ahead and do it. Let's say this point is really 5, 9, and this point is really 4, 2, and this point is 3, 8. And we want to know whether P1 is clockwise or counterclockwise relative to P2 with respect to this point Q. So we calculate the difference between them. For P1, we get 1, 7. 5 minus 4 is 1. 9 minus 2 is 7. For P2, we get, what do we get? -1 and 6. And now we go ahead and compare these two. You can go ahead and put it in this little formula. So what do we get? Which one do you want to, we'll call this one P1. That 1, 7. So what's the value that we get when you calculate this computation? Y1 is 7, x2 is, let's do it. Y1 is 7, x2 is, x1 is 1, and y2 is 6, so you get 6, Negative 6. So that's a negative number. It's smaller than 0. That means this case. And that means the first point should be clockwise relative to the second point with respect to Q. The first point was P1. It's clockwise relative to this, with Q as the origin. Therefore, clockwise in our sense in this example means bigger, so I would use that rather than go this way. If I wanted to make the most right-hand turn, I would move to P1 because it's clockwise of P2. So I've got this very, very basic thing at the very bottom level that lets me choose which one of these angles is the most clockwise or the most counterclockwise. All right, questions about this?
Can we ignore, I mean, if they're equal, is there no more information we can get about one being further out than the other one, which would seem to make a difference for something like Convex Hull?
Sure you could. If there was a tie, you'd just pick the one with, say, the biggest y value. Okay. In this example, because we're going upwards. So you would break ties by the y value. Absolutely. Seth, you have a question?
Yeah. Well, so everything's both clockwise and counterclockwise with everything else, right? So where does this break? You know what I'm saying?
Yes, I do. It's a little annoying when you first see this. That's a good question. Your first instinct should be, well, wait. This is clockwise to this, and this is counterclockwise to that, so there seems like you're not really learning anything. But there is something absolute that you want to learn. If I fix myself here, and I look at all these points, and I simply want to know which one is right of which, that is something absolute. This one is definitely right of this one, and this one's definitely right of that one. You're saying how far to, like, is this really?
Right. There's no absolute there.
Yeah, but when you use the algorithm, if we started to get the home, you're going to be going one direction. You're just going to be trying to make all of the left. You know, you're just going to be scanning one way the first thing to intersect.
As long as, as the first point is on the outside.
Right, so we choose for the first point X max or Y max or X min or Y min, something that's on an edge, and then scan relative to one of the other edge points.
But Seth is asking, we came up with this is clockwise, but why isn't it counterclockwise, just going all the way around this way? So the answer is, think of the halfway point as the, you'd never go around more than 180 degrees. So this is consistent with that 180 degree idea.
So which way is 180 degrees? Clockwise or counterclockwise?
It doesn't matter. If you're going to compare these two and they're less than 180 degrees apart, then clockwise and counterclockwise are distinct. And that's it. So good question. That's important. All right. By the way, I haven't done this outside of the first quadrant. I mean, Heather kind of mentioned this at the beginning. You know, she said, you said, oh, I don't know, we'd have to do different things in other quadrants because there's different signs, right? The x's, and you're just wondering, oh, gee, is it all going to work out? Do I have to do all sorts of different things? Well, this is one of those lucky times. It's like you made something work in the one quadrant, it works in all the other quadrants too. It just happens to be perfect. And if you look in the book, they make a big deal about this, but I won't, but you can look in the book and check it. This is the magnitude of what's called the cross product of these two vectors. So if you ever wanted to know what a cross product was good for, it's really useful to do any geometric algorithms. It is crucial. It is the ABC low-level comparison to check angles is done with cross products and avoids division and avoids trigonometry. So this actually is the definition of the cross product between these two vectors. It's also the determinant of this. Put one point here and one point here and take the determinant of this matrix. That's also this value. So what are determinants good for? They come back here. It all comes together in one big linear algebra circus. Right? So we're not going to get too much into it, but you should realize that that's where it all comes from, and that's where the motivation for it is from. And everything that we're going to do from now on is going to build on top of this. But this is at the very bottom. This is at the foundation of it. All right, questions about this so far? There's a couple more minutes today. We'll finish up. Are there questions about it?
Is everything we do planar?
Yes. Not in general in geometric algorithms, but we're not going to move out of the second dimension because it's too scary. We're flatland people. There's plenty of three-dimensional and multi-dimensional algorithms. Okay. So, before we quit, I am going to go through, not the gram scan or the Jarvis, which will require a little bit of time and having you be a little fresher than you are right now, but I'm going to go through an n-squared algorithm for convex hull. And this is going to be a recursive algorithm that I'll be able to describe once we have this basic stuff down. I'll be able to describe this in 5 minutes. Without this basic stuff down, you'd just be flailing. I mean, you don't even have the basic operations. But with this, we're ready to go. Good, right here. OK. Here's some points on the board. We want the convex hull. Here's my algorithm. I love doing things recursively because I get most of the problem done for free, right? And it's just so easy. So here's how I'm going to do it. I'm going to find the convex hull of this set of points by finding the convex hull of all of them except one, and then figuring out a way to include that one in my answer to all the other ones that had the n-1, right? I could also split it into halves and figure out a way to merge two convex hulls together. I wouldn't be able to explain to you in 5 minutes how to merge two convex hulls together. But I will be able to explain to you in 5 minutes how to stick one extra point in once you get the answer for n-1 of the points. Well, which one of the points am I going to leave out? It's my algorithm. I can pick it, right? That's what's so good. I mean, it's not like you have an adversary here. You can just do whatever you want. So here's what I'm going to do. I'm going to take these points, and I'm going to sort them left to right. So I'm going to leave out the leftmost. I pick it. That's me, right? It's nice because you'll see why in a second. Maybe you see why already. And now I'm going to call convex hull on the rest of the points, recursively. That works by magic. All right, so, okay, so now I get the sequence of points representing the convex hull on the n-1 to the right. Let's write a recurrence equation. T of n equals T of n-1 plus God knows what. All right? So now what we're going to do, we have to take this one, and we take a convex hull and a point and combine them. Well, it looks kind of easy, right? There's nothing to do. What could have happened where I just don't go ahead and say combine? I mean, in this example, it looks like it takes constant time. Just take the convex hull and the point and put them together, right? There's nothing to do. But that's not going to be the case all the time, is it? Here, let me show you a case. Well, you show me. Where should I put points to make this look a little worse and to make it a little harder?
Above the point way up toward the top.
Like here?
Well, leftmost, but yeah. So it's up, yeah, like that.
Well, then that would be here and here. That would still be easy. Right, Mike?
Oh, I
you'd
see.
have to-
Yeah, okay.
Give me an example where, at this point, I'd have some work to do. Like right here, maybe? That's okay? If I had these 3 points here, it would look like this.
Have your left point way above the whole thing.
Right? What if it looked like this? I can't just say combine this with all the rest of these, right? Because look what it should look like.
In the same line that this point, one to the up and one down. Yes, 2 other points.
Okay, good. Right, right. The ones in the middle here, see the ones I just put in that could have been there? I don't want to include them in my overall convex hull. I want to leave them out. How do I make sure to leave them out? Gador just gave me an idea. How do I make sure just to get this one and this one? How do I find those guys? I got a list of all these points. How do I find this one and this one? Right, do that relative clockwise thing. Go ahead on all the points and check. Is this clockwise to this? Is this clockwise to this? Is this clockwise to this? Take the one here that's going to be the most. It's like a crocodile opening up its mouth. You want to hit the most leftwise and the most rightwise. That's where you're going to merge it in. And everything in between gets deleted, and everything on the other side stays in. So it's just a minimum and a maximum calculation. The most clockwise, the most counterclockwise, relative to this origin of all the points on your convex hull. Okay?
Well,
But you aren't guaranteed that that point is outside of the convex hull.
There's no such thing as a point outside of the convex hull.
If the point had been in the middle of the convex hull that you had already calculated.
No, no, but you're not. You're getting a convex hull of n minus 1 sent back to you from the recursion. Oh, you mean like this one here?
Well, the point that you've taken out of it.
Mm-hmm. The 3 points I took out of it.
No, the point that you've got circled.
Yes, yes.
Your external point. If it had been in the middle of your convex
Oh, then this screws up big time. Right. Very good point. Why did I choose the leftmost? Because I know the leftmost has to be on the convex hull. And I know that I can treat it like a crocodile that just wants to open up wide and see the edges. It's like a horizon. What's the furthest point to the right that I can see and the furthest point left I can see? And you're right, Doug, it would not work if this last point was someplace in the middle. I had to control it a little bit. So the way I controlled it is I said, I'm going to make sure the first point I leave out is going to be one that I know has to lie in the convex hull, and I'll pick it because it's the leftmost. This is a very good point, and that's the crucial reason why this really works. Now, how long does this take? Worst case. Tn equal Tn minus 1 plus, how many steps does it take me to do this calculation? You know how to do a clockwise, counterclockwise calculation in one step, but I might have to compare. I have to get the maximum and the minimum of all these numbers. So I have to compare them all to each other and find the maximum minimum. That's going to be order n time. And this recurrence equation, as you know, ends up being order n squared. Now actually, I should mention, there's a better way of implementing this. And if you think about it really carefully, it's one of the star problems in the book. It says, do this idea, but make it run in order n log n. Right? So you can think about that. It's not one of your homework problems, and you don't have to, but it's a good, challenging problem. It's not obvious how to make this run better than n squared. But this is at least our first gut instinct. The key thing that I wanted to motivate with this example is how important it is to have your basic tools. When somebody gives you an algorithm on strange-looking data that we haven't dealt with before, you got to decide what are the basic things you need to do. Make sure you can do them efficiently, and then build your algorithms on top of those things. This orientation check is enough to do a lot of geometric algorithms. Okay, questions about this?
But just in the recursion, you're going to go with n minus 1 and then take the leftmost of that. But that's not that be necessarily on the convex hull, is it?
Just on the convex hull of everything except the other point.
The next left is going to be on the convex hull of these points to the right. So the way the recursion actually unwinds is you start with the 3 most right points, and you find their convex hull. And then you back up and add the next one that's leftmost in, and the next one that's leftmost into that. And the last step is you add the leftmost one here into the whole convex hull. So you build the convex hull out this way. So it's okay, but there is one issue that nobody mentioned. It's a technicality, but you should mention it. What is that?
What about 2 points on the same vertical line?
Yeah, what if I have 2 points right on top of each other? So there isn't a leftmost point. What if I have a point here and a point here?
Choose a different starting point.
Oh, I guess I could just try it. But what if any way I try, it always ends up with some kind of issue like this? Yeah.
Put them both on and take it.
They're both on the convex hull, right? So
So I can just do one at a time. It doesn't matter what order. It's perfectly fine to do them in any order, and you will still get the right answer. So it's a technicality which just is no trouble at all. Okay. Sometimes this technicality requires kind of a subsorting. You know, if there's a tie, go to the highest one. And the other algorithms we'll talk about will have to do that. They do have to distinguish between ties. But this algorithm is so kind of brute force-ish, almost anything works okay. Yeah, Tony.
Would it be possible to, like, divide? Did you mention the possibility of dividing it into subproblems? Like, could you pre-sort the points?
Yeah, sure. There's a lot of different ways to do it. You can pre-sort the points. You can split them in half. There's a lot of different. There are, I wouldn't say as many, but there are almost as many ways to solve convex hull as there are ways to sort numbers. Okay?
I figured since you said log n that you'd have to do some kind of splitting.
Right, right. You could also might think of a heap idea in order to, I mean, what are we really doing here? We're getting the min and the max, right? That should scream, maybe there's a way to do it with a heap. It isn't obvious because every time you get the next subproblem, you have to kind of rebuild the heap from scratch because all the angles change. But maybe there's a way to do that and update it as you go. Yeah, Rob.
You could eliminate internal points to your figure in various ways,
Right, there might be some pre-processing you could do to shorten it up, possibly.
What if you just used your counterclockwise or clockwise algorithm to determine right turn-in-this and left turn-in-this and traversed the points that were to the outside of the group? And then after you were done, go back and post-process all your right turns, say, and back up your initial point until you...
That's a good idea. That's a really good idea. That's a little bit like Jarvis's algorithm, sometimes called the gift wrapping algorithm. You kind of put a piece of tape here and try to wrap as tightly as you can around. It's a little like that. One little thing before you go. This is n squared. I told you you can do n log n. Nobody has a linear time algorithm for convex hull. It'd be nice to know if it was possible to do that. Same with sorting. But it's not. And I'm going to convince you it's not really quickly without any decision tree. This is a famous example of a reduction, something we'll be going through a lot in the last week. How am I going to convince you of this? I'm going to convince you that if you could solve convex hull problem, then you can sort numbers. And you can't sort numbers faster than n log n. So there's no way you're ever going to solve the convex hull problem faster than n log n. Okay, I'm going to convince you that if you come up with an algorithm and come into my office and say, I got a convex hull algorithm, I can use it to sort numbers. Okay? Here's what I'm going to do. Say I got a bunch of numbers, 8, 15, and 3. And I need them sorted. And it's causing me a lot of grief. I need these numbers sorted. But you got a convex hull algorithm. So here's what I'm going to do. I'm going to take the numbers, and I'm going to turn them into points. I'm going to take every one of these and make it an x-coordinate and use its square as the y-coordinate. So this will turn into 3, 9. This will turn into 15, 225. And this will turn into 8, 64. And if I had a million more, say 1 will turn into 1, 1. And 6 would turn into 6, 36. I got these numbers to sort. You got a convex hull algorithm. Peanut butter and chocolate. I give you these points. I say, run your convex hull algorithm for me. What are these going to look like? These are going to be points on a parabola. Right? A parabola y equal x squared. What does a parabola look like? This particular parabola, y equal x squared, looks like this, right? I take my points that I want to sort, and I plot them on the parabola. And I give them to you, and I say, find me a convex hull. What are you going to give me back? You're going to give me this. You're going to give me an ordering of these points along the convex hull in clockwise or counterclockwise order, and that'll be exactly the order that they're sorted in. 1, 3, 6, 8. So all I have to do is take my numbers, stick them on a parabola, give it to you, say, do your convex hull. When you're done, tell me the answer, and you've sorted my numbers. So if you've got a linear time algorithm for that convex hull, then I've got a linear time algorithm for sorting. Because it only takes me linear time to do my reduction, and then it takes me linear time to use your thing. So this reduction actually proves not a good result, but a bad result. Since I've reduced sorting to convex hull, I've reduced it. I've showed you that convex hull is at least as hard as sorting. Because if you can do convex hull, you can do sorting. Therefore, convex hull is worst case, got to be lower bound, n log n. Is that the question?
Does the reverse hold true? I mean, can you reduce it the other way? So, like, if you know stuff about your numbers, can you do like a bucket sort on them and then have it run in linear time, that sort of thing?
Are you asking, is there a way to reduce convex hull to sorting?
Yes.
No, not that anyone knows. Convex hull is probably harder than sorting in some ways, but I don't know. I'm going to back off and say I don't know, because maybe there is a way to reduce convex hull to sorting, and I just haven't thought about it enough. But I don't think so. I mean, the reduction in this direction is kind of easy, and I'm not sure there's a reduction back the other way. I don't know. It's a good question. Reductions are the key to showing problems are either hard or easy, depending on what direction you reduce. And we'll talk a whole week about it. So it's a little preview, and it's a really nice result here. All right. Any other questions? All right. We'll do gram scan and Jarvis's algorithm tomorrow. Then we switch gears, talking about techniques.